So I guess I will proceed. Feel free to move closer to the front if you'd like, because as usual, there's vast spaces right in front here. So I'm Donald Eastlake. I'm the co-chair of the IETF TRILL working group, and I'm going to tell you about RBridges and the TRILL protocol. So, just a brief note that this is a kind of a high-level overview. I do have 90 minutes, but even so, there's plenty of stuff that I won't be able to cover. This is going to be the rough outline of the talk. Some introductory things and talk about various features and aspects of things. So, what is it? Well, TRILL is a new standard protocol, does layer 2 bridging using ISIS link state routing. Really uses routing and manages to accomplish transparent bridging with that, which is a good trick. It was invented by Radia Perlman of Intel. If people have any difficulty hearing me or whatever, they should certainly tell me or stick up their hand or something. She's pretty well known. She invented spanning tree, something you've probably heard of, some long time ago. She did lots of contributions to link state routing. She also invented DECnet Phase 5, and ISIS, which is an ISO protocol, although it's really primarily maintained by the IETF these days, is really just a copy of DECnet Phase 5. So really, she invented ISIS as well. So TRILL stands for Transparent Interconnection of Lots of Links, so typical IETF cute backronym kind of thing. I think they thought of TRILL first and then figured out what it stood for. But anyway, I'm a co-chair because Eric Nordmark of Oracle is the other co-chair. And what is an RBridge? An RBridge is a routing bridge. It's a device which implements the TRILL protocol. And there's also the term RBridge campus. So an RBridge campus is a network of RBridges, these devices, with links between them. And they may also have bridges in there. And it's bounded by end stations. So basically, an RBridge campus is to RBridges the same as a bridged LAN is to bridges. So basically, it's a very simple idea. I think most great ideas are simple. You take native frames, the ones you're trying to get shipped around and bridge, and you encapsulate them in a transport header, which includes a hop count. This is called the ingress function. Then you route those using ISIS routing. I'll give all the details, but that's sort of a transit function. And then ultimately, you just decapsulate the original native frame transparently and deliver it. And that's the egress function. But of course, there's a few complexities in the details. So why was ISIS chosen? I mean, this is done by the IETF. The IETF came up with OSPF, which is another link state routing protocol. So why didn't they choose their own link state routing protocol effectively? And there are two main reasons. First of all, ISIS runs directly at layer 2. So you don't need to configure RBridges with an IP address. In the real world, one would expect most RBridges to have an IP address for management or some other reason, but it's not needed. They can come up, find each other, establish the topology, do bridging fine with no IP addresses or even no IP traffic anywhere in sight. And this sort of fits with the minimal configuration goal, or at least the ability to work with minimal configuration, which is one of the goals of the TRILL working group. And secondly, ISIS has a very flexible data format. So you can, in the control plane, encode new kinds of things easily using a type length value encoding. And those are the reasons that ISIS was chosen. So what features do you get with this TRILL thing here? Well, there are quite a few. One is optimal point-to-point forwarding. So here we have a little network, 3 bridges, a bunch of end stations. So we use spanning tree, and by golly, spanning tree works by turning off ports. So you got this link, which you sort of paid for something to do with that link, and you can't use it really. And frames are not following optimal paths. So those between B2 and B3 have to go via B1. That's not too good. So you can just replace those bridges with routing bridges, RBridges, and there you go. You get optimal routing. All the links are used. Things follow the shortest path. And if you don't have any VLANs configured or nothing else, you could do just this with no configuration. Just replace the boxes, and there you go. Multipathing is another feature it provides. Multipathing is optional, but I don't know of anybody implementing TRILL or RBridges that is not going to do multipathing. So with spanning tree, to avoid loops, you really can't have multipathing. Frames from B3 to B2 in this diagram really can only go one way. If you tried to do multipathing for different flows or something, things would get very confused. If RB2 is actually a bridge, it would be getting frames with the same source address from different directions. But with RBridges, it all works fine. It can do multipathing, and you get higher bisectional bandwidth. The traffic is spread over your links better. And for a slightly more data center-ish looking diagram, this is a kind of reduced number of boxes just to get it to fit. A spanning tree with lots of links disabled, you may only have one path between a couple of these bridges at the bottom. But with RBridges, you can have multipathing, can spread different flows over different paths. And as initially designed, RBridges work fine with, this could be very wide, could be 200 wide, for example. You could have 200 alternate paths. No problem at all with TRILL and RBridges. What are other features? Well, they're compatible with classic bridges, so you can incrementally deploy them into your bridged LAN. The recommendation is that you deploy them in such a way as to break up your bridged LAN into small islands. That is to say, you reduce the size of the spanning tree. It's based on the theory that spanning tree is not really that good, especially as it gets bigger and bigger. So if you are going to have a mixed network, you want to deploy the RBridges so as to reduce the size of your spanning trees. And probably the worst thing you could do would be to have a whole bunch of RBridges right next to a whole bunch of classic bridges with lots of connection points between them. That would not work nearly as well as placing the RBridges at the key high connectivity spots inside your bridged LAN. The unicast forwarding tables of the transit RBridges, they scale just with the number of RBridges. The transit RBridges, ones out in the middle, really just have to know how to get to other RBridges. They don't care about end stations. The transit RBridges in the middle don't need to learn end station addresses. Only the edge RBridges, those with directly connected end stations, need to learn end station addresses. It has a flexible options feature. And then one interesting thing is that RBridges know what options other RBridges support. So they can tell before sending a frame to some other RBridge whether it'll support that option. It's got features, optional features for optimized distribution of multicast. And it generally can do a better job of optimized distribution of multicast than bridges can. Classic bridges, even though those which do snooping and do this sort of thing, which is not really a normal bridging function under the bridge standards, they do it based on local observation of traffic, local observation of group membership messages and stuff like that. And so if there's a topology change somewhere else, they can't really adjust the multicast flows for some length of time until the soft state refreshes come through. With RBridges, they actually know through the topological knowledge, they get reports as to where there were multicast listeners, where there are multicast routers, things like that. So if there's a change in topology, they can immediately change the distribution of multicast frames so as to get the frame where you want, but still optimize distribution. So I have a couple examples. They're fairly small examples, but you might be interested in them. So this is actually sort of a process control application example. I have a data center application right after this example, right after this. And this is a case where there was a process control protocol that couldn't be routed, so you had to do everything with bridges. And actually, there's the embarrassing fact that the way the protocol was set up and stuff, the legacy protocol, if you lost connectivity for more than 1 second, it would assume there was a failure. And there have been nuclear power plants which shut down due to the root bridge failing in the control system for the nuclear power. And when that happens, you have to write lengthy reports to the government. It's really not pleasant. So what can you do about that? Well, one thing you could do, here we have this network here. We have sensors and effectors and control valves, who knows what, around the edge. Or this could be some other application that had the same structure. It would really be much larger than this. And if we're running spanning tree, lots of stuff gets shut off, not used. But we can just try replacing just the 2 core bridges with RBridges. And zap, you've immediately broken your STP domain into 3 much smaller domains that'll settle faster, be more, you really get much better performance. And let's say you want to go a little further. The aggregation bridges around the edge and the access bridges are also bridges. Just replace the center 2 boxes. Let's say we want to replace these GB aggregation bridges with RBridges. Well, if we do that, we can actually eliminate the core bridges because RBridges are really good at handling a mesh and distributing things. And at this point, we've reduced the size of all of our spanning tree domains to 1 bridge. And a 1 bridge spanning tree domain actually is very well behaved. So that's one example. Here's something that might look familiar for like a small data center kind of thing. So we got a bunch of Keta rack bridges and some distribution bridges and some routers here. And we have limited numbers of paths between the racks and stuff. And really, we're only using one of these distribution bridges. And the distribution bridges better be damn reliable. I mean, if you take one down for maintenance, the other one is like all you're depending on. So they have to be able to handle 100% of your load. They got to be very well engineered. They're probably expensive. But if we're willing to use RBridges, we can have a bunch of them at that level. We get multiple paths. This has RBridges for the distribution level and for the head of rack. We can have a bunch of them. We have multiple paths between the racks. This way, we have each one only has to be able to handle 25% of the load, and you can still have one out of service or failed. And even if the second one failed, you would just get degradation. It wouldn't be nearly as bad. So that's just some of the simple things you can do in a very small scale. So basically, bridges have a lot of great features. They're transparent, plug and play, great stuff. They implement virtual LANs, useful for security and other things. They have frame priorities. It's a good thing. And kind of leveraging off the frame priorities to label different kinds of traffic for effectively different pipes. There's the data center bridging, which I have more on later. And currently, there's under development a bunch of virtualization support called edge virtual bridging. These are all great things about bridges. But, routers have a lot of good features, too. They're really good at multipathing. They're really good at optimal paths, rapid failover, stuff like that. And they have the safety of a TTL. So, a lot of people will say, well, I can prove this system works properly because I can prove the control plane and control algorithms are all work great. And you say, well, what happens if the control plane isn't functioning? Because as control planes get more and more complicated, you get the control plane crashes and the data plane keeps operating. It's not clear that these proofs are as good in that case. And typically the TTL reduction in this guard of frames where the TTL counts down is done in the fast path. So even if the router control plane crashes, the safety of a TTL can save you. It's pretty good. And typically routers have protocols that have options and things. So RBridge is really a great combination of the best of both of these. So the way the TRILL encapsulation header works, what I'm going to talk about next. I mentioned these native frames are initially encapsulated. So between RBridges, once it's been encapsulated, there's a local link header and a TRILL header. And this local link header is really just intended to get that frame over the next hop, get it to the next RBridge. And if it's a unicast frame, it's a unicast address to the next RBridge. And if it's a multicast or multi-destination frame, broadcast or something, it's then sent to the all RBridges multicast address. So if there's multiple RBridges over that link downstream, it can get to them. In this frame, there's a TRILL header, and that specifies the first RBridge that was hit, the ingress RBridge, and either the last one that's going to go, the one it's aiming for, is where it'll be decapsulated if it's unicast, or if it's a multi-destination frame, that egress RBridge slot is really the name of a distribution tree on which that frame is going to be distributed. So just to back up for 1 second and talk a little bit about different kinds of frames. So in one of these RBridge campus, there are really four kind of frames. There's the TRILL ISIS frames. Those are used between RBridges for the control. TRILL data are these encapsulated native frames, the ones that are being routed. There are also layer 2 control frames, of course, local link discovery protocol, MACsec, who knows what. And those are really just over mostly over a single physical hop. Anyway, in any case, they're never forwarded by an RBridge. RBridge can implement all these things in the port. The RBridges are really built on top of 802.1q ports. So anything that you can do in the port, you can do in a port on an RBridge. And then there are the native frames. There's something which isn't one of the above. Those are the frames that are really to or from the end stations, and the ones that haven't yet been encapsulated or decapsulated. So actually in a little more detail, TRILL frames are ones that have the TRILL ether type. And as I say, they're either unicast addressed or sent to the all RBridges multicast address. Or the control frames, which have the layer 2 ISIS ether type, they're always sent to the all ISIS RBridges multicast address. And actually there are some other things that are classified as TRILL frames because there's actually a whole block of multicast addresses reserved for TRILL. These other frames are not yet used. They're available for extensions to the TRILL protocol. Layer 2 control frames are identified by the destination address in the bridging block of 16, or for purposes of TRILL, the address 180C20021. And the ones that are BPDUs or VLAN registration ones are handled a little differently in RBridges from bridges. Spanning tree never runs through an RBridge, so RBridges always terminate the spanning tree. But if you want, you can have your RBridge port participate as a leaf in spanning tree. If you have an RBridge connected to a bridge LAN and you want your RBridge port to be the root bridge, or to look like the root bridge for that bridge LAN, you can have your RBridge port participate in spanning tree if you like. It's an option. All the other layer 2 control frames, as I say, are really things that happen in the port, and you can implement them in the port of your RBridge if you want, but they aren't ever encapsulated or transported. So this is what things look like. You got this assumes you're going over an Ethernet link, which is pretty common. So down at the bottom we got a couple of RBridges, and they could just be connected by a wire, or they could be an arbitrary cloud of 802.1d and Q bridges and who knows what in between them. So the original frame is in this encapsulation. There's it's over here. There's the TRILL header in front of that, and then there's this link header, which is to get it over the next hop. And for Ethernet, you need to have a destination and source MAC address and a frame check sequence on the end. And this shows a VLAN there, which is just for the general case. If you have just a piece of wire between two RBridges, there's no reason for this outer VLAN. The actual VLAN of the data, the actual VLAN of the native data, is preserved inside the original frame, inside the encapsulation. And this is really the same thing in text, so it's not too interesting. So I'm actually going to step through what happens for a unicast frame when it's ingressed, forwarded by a transit RBridge, and then egressed. So here we have this input native frame, and it's shown there with a VLAN tag. Of course, it might not actually have a VLAN tag. It could be untagged, but RBridge ports, as I say, are 802.1q ports for most purposes, and they do assign a VLAN and a priority to every incoming native frame. So by default, it's default priority and VLAN 1, but depending on what features you have at that port, could be something else. So if that wasn't originally there, it gets added logically by the port as the frame comes in. So we take that original frame, less the frame check sequence, and we're going to encapsulate that. So the next thing we do is we add the TRILL header. We take the destination MAC and destination VLAN and go look it up. So that gives us information, including what the egress RBridge is going to be. We know what we are the ingress RBridge, so the ingress field there is something easy for us to add. We pick what we want the TTL to be, and then we label it appropriately for the link that's the next hop. And assuming it's an Ethernet link, which is most people think, we add a new frame check sequence on the end, and our own source address and the destination MAC address of the next hop. And there's a place for an outer VLAN tag. So that outer VLAN tag is generally not needed, certainly not if you have point-to-point links. But if you have, if this next hop to the next RBridge is actually something involving carrier Ethernet facilities that restrict your VLAN, or actually a bridged LAN that has VLANs configured so only certain VLANs will get through or something like that, you might need the outer VLAN tag there. Okay, so now we have this original frame all encapsulated, and we arrive at a transit RBridge. And in that case, what we do here is we essentially extract the information. We throw away the link header and the FCS, pretty much. We decrement the TTL. If it's 0, we throw it away. And we figure out how to forward it, and that really only depends on this egress information. So we just forward it RBridge hop by RBridge hop to the egress. So just look that up and figure out what the next destination address and output port is and send it out. So eventually we get to the egress RBridge, and the egress RBridge can recognize that because it matches the egress field in the TRILL header. So when that happens, we extract the original frame again, and we still have the original VLAN information. And then we look at the VLAN and destination to figure out the output port, and whether this VLAN tag here, the VLAN superscript 2, will actually be on the wire when we send it out, just depends on the configuration of that output port, the way it would on the output port of any 802.1q bridge. We can strip VLANs, or we can send it VLAN tagged out the port in native format if we like. So this is the details of the TRILL header. This shows it with an ether type. There's a TRILL ether type. That's actually only necessary on Ethernet or Ethernet-like links. If your link was a PPP link or something like that, you wouldn't need the ether type. You'd have the indications of what the frame was. There's a version, currently 0, and some reserved bits. There's one bit that indicates whether this is a multi-destination or unicast frame. There's a option length field, which is 0 if there's none. 6 bits is the hop count. So you can tell 63 is the biggest hop count you can have. Then there are these nicknames. So nicknames are actually 16-bit abbreviations for RBridges in most cases. And they're auto-configured. You don't have to worry about that. The RBridge campus comes up with these all by itself. And the ingress RBridge nickname is always really the nickname of the RBridge that received the initial native frame, the one that encapsulated it. For unicast, the egress RBridge is really the nickname of the RBridge that's going to decapsulate it or egress it. But if it's a multi-destination frame, then the egress RBridge nickname field is actually the name of the distribution tree that the multi-destination frame is going to be distributed over. So this encapsulation does lots of good things. You provide the space for the hop count, lets you hide the original source address, so when you're doing multi-pathing, you don't get confused bridges seeing things coming from different directions with the same source address. It gets the frames towards the egress and permits you to decrease the size of the forwarding tables. They only have to look up the nickname of the egress RBridge. And provides a place where you can use this outer VLAN tag, which you might need. So as this transit RBridge, a transit RBridge that's forwarding a frame could receive it if you have lots of funny restrictions where you have to do a lot of outer VLAN labeling, could receive it with an outer label in one VLAN, VLAN X, and forward it with an outer label in VLAN Y, even though the real data inside is really VLAN Z data for a third VLAN. Because it's just getting the stuff through, and the VLAN restrictions are really only enforced at the egress RBridge. That's where it matters. That's where you're changing it back into a native frame and sending it to an end station. So these strange things, they really bridges or routers. So there's a bunch of reasons why you say these things must be bridges. They deliver unmodified frames, just like a bridge does, right? They operate with zero configuration. You can plug them together and it all works, plug and play, just like bridges. They do enforce VLAN restrictions, same way 802.1q 2005 bridges work, pretty close. There's one exception I'll cover later. They do support frame priorities, They learn MAC addresses from the data plane. I'll get into that, just like bridges do. So they're obviously bridges, but maybe they're really routers. Okay, they do swap the outer addresses on each RBridge hop, just the way routers swap outer addresses effectively. They decrement a hop count, discard the frames if the hop count gets to 0. They really use a routing protocol. They use ISIS not just to determine the topology, but really for the forwarding and routing. They learn MAC addresses. They can learn MAC addresses through the control plane. There's an optional protocol I'll talk about later, which can do that. And they do these various things related to snooping on various multicast group control messages and things like that, which admittedly some high-end bridges do, but really seems much more of a layer 3 kind of thing. So I think they're pretty much, more routers than bridges, but they're really, when it comes down to it, about layer 2.5, they're a new kind of thing. So in current networks, you can have routers and you got bridges in between them, and actually you could have, hubs and repeaters and stuff like that between bridges. And they could go between routers. But now you have these RBridges, and they're really a new layer in this hierarchy. And you can put them between routers, works fine. You can put hubs or repeaters or bridges between them. And if you look at this stack, essentially to each of the things in this stack, pretty much things below it are transparent. To routers, all this stuff is pretty transparent. To RBridges, bridges are transparent. But if you look up, it's not true at all. So bridges, looking up, RBridges terminate the spanning tree. They look just like routers to bridges pretty much. And to RBridges, looking upwards, routers terminate the RBridge campus. So they terminate the TRILL protocol. So that sort of has implications to how things peer. If you have a couple devices disconnected by a piece of wire, if they're the same kind of device, whatever they are, bridges, routers, they can peer pretty well. But when you get things in between, it's not so simple. So if you've got a couple routers or something with bridges between them, they can peer because the bridges are transparent to them. But bridges can't peer through routers generally because the routers block all the bridging messages. And the same sort of thing might be true even another layer if you have provider bridges or something. But with RBridges, you have this new layer. So routers and end stations, they can peer through all this RBridge and bridge stuff in the middle. And RBridges can peer with each other despite bridges in the middle, but you really can't have other kinds of things. RBridges can't peer through routers, generally speaking, and bridges can't peer through RBridges because RBridges block the spanning tree BPDUs and so forth. So I'm going to go into some more details on how they actually work. I think we're doing pretty well on time, so hopefully we'll have a bunch of time for questions at the end. So the first thing when RBridge comes up is it starts sending TRILL ISIS hello frames, and that's how the RBridges find each other. So like all of the TRILL ISIS control frames, they're sent to a multicast address, all ISIS RBridges, and these would be transparently forwarded if there were any bridges in the way. You might have all point-to-point. There might not be any bridges, but if there are, they just forward them. If they hit any end stations or routers, they would normally not be configured to do anything with that multicast address. They just drop the frames. And when these frames hit an RBridge, these TRILL hello frames, they're processed by that RBridge, but they're not forwarded. So these TRILL hellos are actually a little different from layer 3 ISIS hellos. That's because they're smaller, unpadded, and they support fragmentation of some of their information. The layer 3 ISIS LAN hellos are always padded up to, you can configure something else, usually padded up to the Ethernet maximum. You can configure things to be a different amount. And that provides a useful function of checking the MTU, but for TRILL there's other separate MTU probe and ACK messages that are provided for MTU testing and determination. And there's a reason for this, because it's actually pretty important for TRILL hellos to get through, which I'll cover on the next slide. So anyway, using the information exchange in these hellos, the RBridges on each link select one RBridge on that link, called the designated RBridge. And that link, you'd think that if you do only point-to-point hard physical connections, then it should be very rare for there to be a multi-access link. But if you do have any bridges involved, let's say you just have a peripheral bridge with a bunch of end stations connected to it, and you decide to have that bridge dual homed to two RBridges to provide transport inside your extended local area RBridge campus, then because there's a bridge between these two RBridges, they can see each other and they can see all the end stations, and it looks to the RBridges pretty much like a multi-access link. And in this case, the two RBridges, one of them would get automatically elected the designated RBridge for that link. So let's talk a little bit about these TRILL hellos and why they're limited to a maximum of 1470 bytes. The point is it's actually important for the RBridges to be able to see each other. So we have a little diagram here with two devices and a cloud between them and a link between them, and it says low MTU device. But let's assume for a second these devices were actually bridges. And whatever this device in yellow was, it had the effect of filtering BPDUs. So BPDUs didn't get in. Well, these two bridges couldn't see each other. If they're running spanning tree, they would really not have any way of knowing that that link sort of was between two bridges. And let's assume that some device out on that link emits a relatively small, or somewhere else in the network, emits a relatively small broadcast frame. Well, that broadcast frame could go out one side of the link, over here, and it would just go, if it's small, it would go through and be picked up on the other side, and then it would cycle around through the spanning tree and be re-emitted, and you'd have a loop. So if you have, obnoxious enough devices, you can have problems like that. And TRILL wants to be sure that the RBridges can see each other, so it will know that there's more than one on this link, and they can arbitrate appropriately and avoid loops. Only one of them, it wants only one of them to be the designated RBridge, and that's the one that's going to figure out who's going to handle native frames for each VLAN. So anyway, so moving on how RBridges get their act together, they've sent out these hellos and established adjacencies, and then use the ISIS reliable flooding protocol so that each RBridge gets a copy of the global link state database. From the name of that, you can tell it basically tells who's hooked to who, where there are links, and it has the cost of those links, basically the inverse of the bandwidth typically. But you can have other things in there which are distributed, and for RBridges it includes a number of other pieces of information such as what VLANs each RBridge has an end station connectivity with, where there are multicast listeners and multicast routers. It's used for the nickname arbitration. It's how the unique nicknames are derived for each RBridge across the campus, what options are supported, and so on. So using this database, which will, in a stable network, they'll all end up with the same copy. That database is sufficient for each RBridge to independently, without any further messages or anything, calculate optimum point-to-point paths, and also so they all calculate the same distribution tree or distribution trees for use with these multi-destination frames that you have. So the designated RBridge on each link specifies what are called appointed forwarders for each VLAN on that link. By default, the designated RBridge is the appointed forwarder for all VLANs by itself, but if it wants to load split, it can designate some other RBridge on the link to handle traffic in a particular VLAN. It also specifies a designated VLAN for inter-RBridge communication. So, as I say, the appointed forwarder handles all the native traffic for a particular VLAN. The appointed forwarder stuff has no effect on TRILL data frames, as ones that are already encapsulated. Those are any RBridge on the link can send or receive those. And so the appointed forwarder is one that encapsulates frames from the link, doing the ingress, and decapsulates frames onto the link or the egress for the VLAN or VLANs for which it's been appointed. So why is there this designated VLAN thing? In the general case, links between RBridges have a designated VLAN. It's dictated by the designated RBridge for the link. If you have point-to-point links, you don't ever need an outer VLAN tag really on a point-to-point link, and if they're configured to be point-to-point in the ISIS sense, then you don't even need it. There really isn't a designated VLAN. But if you do have there are other cases where you really need this outer VLAN tag, and you need a designated VLAN ID to make sure that TRILL data can be communicated between the RBridges on the link. So one thing I think I mentioned before, if you have carrier Ethernet facilities that limit you to some VLAN, the link is actually a bridged LAN, which has a bunch of VLAN restrictions, or if, since the RBridge ports are 802.1q ports, you can in principle configure the RBridge ports to restrict VLANs. So if you have any of these things, you need to, you need to have a designated VLAN, which is one used by the RBridges to communicate on that link. So TRILL data frames, if they have a known unicast destination, they're just forwarded RBridge hop by RBridge hop with standard routing techniques to the egress. If they're multi-destination frames, include broadcast, multicast, and unknown destination unicast, they're forwarded on a distribution tree selected by the ingress RBridge. So for loop safety, the multi-destination frames are subject to a reverse path forwarding check as they're received by each RBridge, because they're a little more dangerous because they can fork. The distribution tree can have forks, so you get multiple copies of frames. So you want to be particularly careful about them. And you can prune the trees. What it really means is an RBridge can decide not to send the frame down some branches of the distribution tree. And it would do that because it looks at the VLAN of the data, say, and it says, oh, this is a VLAN 7 frame. I know that from the link state database, I know that down this branch of the distribution tree, there aren't any listeners for VLAN 7. So there's no reason to send the frame down that branch. And similarly for multicast groups, if there's no multicast listeners, it doesn't need to send it down the frame. So one way in which RBridges do treat VLANs differently, and it's probably the only real way, it tries hard to glue together all end stations that are in a particular VLAN. If you're in an RBridge campus and you've got two end stations and they have connectivity to an RBridge, presumably different or ones, then they will be able to communicate with each other. So if you had a bridged LAN and you went through and you replaced all the bridges with RBridges, if you had VLAN islands, if you had configured this bridge LAN by configuring the VLANs on the ports in such a way that you had VLAN islands, when you replace those bridges with RBridges, TRILL will glue all those islands together, which might not be what you wanted, or might be, maybe it was what you wanted. So talking to customers, many of them found that it's really kind of desirable not to have VLANs partitioned, but obviously there are cases where you do want to be able to do that sort of thing, and you want to have the same VLAN ID in different parts of your RBridge campus actually mean different things, maintain islands, or perhaps different VLAN IDs in different parts of your campus really be connected together and mean the same VLAN. So there is a feature that will do that, where you can divide your RBridge campus into regions, such that the VLANs actually in priorities in the different regions can be mapped or blocked in various ways at the inter-regional boundaries. So essentially it makes the meaning of VLANs and priorities kind of local to each region. So this is done in such a way that any of the RBridges internal to a region don't need to know anything about this. They can just ignore the whole thing. And a question you might have is, well, that's sort of interesting, but since these RBridge ports are 802.1q ports, why isn't all the normal bridging facilities for doing VLAN ID mapping or priority regeneration or stuff like that solve your problem? And the answer is, it's because of the TRILL encapsulation, that the true VLAN ID and the preserved priority are in the inner frame. So you need to have a facility where you can change those inner values. So here's a couple regions and 3 border RBridges. So there could be lots of RBridges in each region, and they wouldn't need to know anything about what was going on. But by configuring these 3 RBridges on the border, you can cause the same VLAN ID to effectively mean different things in the 2 regions, cause frames in some VLAN to be dropped from both sides so as to maintain 2 separate islands or so forth. And on each of these RBridges, every port has to be configured as to which region it's in. You can have more than 2 regions too, it's just that it's simpler to talk about with 2 regions. And each RBridge has to have every port configured as to which region it's in. That even includes cases like the link shown between RB2 and 3. You say, well, this is a link between 2 border RBridges. It's sort of it's just a point-to-point link, perhaps. It's like in neutral territory. Why does it have to be configured to be in one specific region? And the answer is that if you look at that piece of wire, whatever it is, fiber, whatever, the TRILL data frames on that piece of wire have this inner VLAN tag that has 12 bits of VLAN ID and 3 bits of priority. And with multiple regions, a VLAN ID and a priority don't actually mean anything unless you can say what region they're in. Because it could be that if in a different region, they would be mapped to some other value or even discarded or something. So in this case, that link between RB2 and 3 is shown as being in the east region. Could be in the west region, but both ends have to be in the same region. They have to be configured for to be in a specific region. So this mapping that I've talked about is all you need to do to solve everything for unicast addresses. I won't go into the details, but it works for both learning from the data plane, addresses and VLANs. It works for the control plane transmission of VLANs and addresses and so forth, the control plane learning. However, there is a little bit more you need to do for multi-destination frames. And the reason for that is because of this tree distribution pruning. So you have to be sure that border RBridges get all the frames that they might need to map into the other region. So for example, if a border RBridge is mapping between VLANs X and Y, it has to say that it's connected to both of them. Otherwise, a frame in VLAN X might get pruned before it gets to that RBridge, even though on that branch of a distribution tree, there is a listener in VLAN Y downstream in the other region. So you actually have to set things up so that the border RBridges will advertise connectivity in such a way they get all the frames they need to translate. And the same kind of thing is true for multicast groups. One point about all this is the whole campus still operates as a single routing area. Nothing to do with this has any effect whatsoever on the shortest path calculations, the distribution tree calculations, or anything like that. The frames follow exactly the same RBridge to RBridge path that they would have before. It's just that when they pass through a border RBridge, then the VLAN ID and the priority of the data can be mapped. So you get all the same advantages. It doesn't reduce the effectiveness of the shortest paths or whatever by doing separate optimal paths in each region or anything like that. It's all still one RBridge campus. I'm going to go in a little more detail on what actually sort of happens when a frame hits an RBridge internally in terms of the port structure and so forth. So here's a kind of nice generic diagram. Could be almost anything, a bridge or router or whatever. It's got port logic, it's got switching fabric, it's got control logic. What more could you ask for? Anyway, and of course the links at the bottom could be Ethernet or Wi-Fi or whatever, PPP, who knows. So looking inside effectively a port on an RBridge, we have some kind of physical interface. Shown here is an Ethernet, 802.3. We got low-level control frame processing and port link stuff. So this is where you would implement lots of stuff that's just, a MACsec, for example, who knows, or LLDP, or things that are kind of part of the low-level control stuff. And then if you're familiar with the bridging standards, there's this interface called the Internal Sublayer Service, ISS, and the extended ISS. So that's shown here. Between the ISS and the EISS is where this VLAN blocking or admission and classification of all incoming frames to a specific VLAN and stuff like that happens. So everything shown in blue here is the same on an RBridge as it is on an 802.1q bridge, except for in some ways, perhaps depending on this year's structure, the way BPDUs and VRP frames are handled. And the reason there's some special handling there is that RBridges, although they block spanning tree and they don't normally participate in it, they are required to monitor BPDUs. So look to see if there's any BPDUs coming in. And the reason for that is that if you have a multi-bridge LAN connected to it and the root bridge changes, this could be an indication that there's some topology change or things going on out there. Let's say, for example, you had two RBridge campuses, got RBridges, and both these RBridge campuses also had bridged LANs that are part of them or connected to them. And you then decide you want to merge these two campuses by plugging a cable in between two bridges. So suddenly these two bridged LANs, which are part of these two different RBridge campuses, have become one bridged LAN. And actually the two RBridge campuses have now become one RBridge campus, but they don't necessarily know it yet. Well, when these two bridged LANs merge, the one with a higher priority route won't see any route change, but the one with the lower priority will. And while things are getting sorted out, you might have multiple RBridges which are now connected to one link. And so RBridges need to be a little bit careful about that and be aware of it. You can avoid these problems by not having multi-bridge bridged LANs. If you have a single bridge being used as an access bridge or whatever, that's never a problem. Because, I mean, even in some literal sense, it's always its own route and it never changes. Or you can just make everything be RBridges, which will actually work better, but that's up to you. So anyway, so this is what's happening at the very lowest level. On this diagram, the orange lines show information. The gray, thicker lines show frames flowing and can also indicate information flow. So, so over on the right here, these frames that get through the port VLAN processing up above the EISS go up to higher level layer processing. So what happens at the higher layer? So the frames coming in at the bottom here, this little orange diamond, they get divided up in different categories. So let's look at TRILL ISS hellos, go straight up there. Process, the TRILL ISS hello processing is really port local for most practical purposes. You can arrange your structure however you want as long as it all works the same, but I think this is the most logical way to look at it. There can be native frames coming in or going out, and they go over to the left. So if a native frame comes in, there's various tests done. And one is the RBridge says, am I an appointed forwarder for the VLAN this native frame is in? If I'm not appointed forwarder for that, I just throw away the native frame that came in. If I am an appointed forwarder, then I encapsulate the frame and it goes up the left side up to the higher layer logic. Similarly, there could be data frames that are to be intended for local delivery that come down the left side. They get decapsulated. They can also go to this appointed forwarder logic. So it's unclear why they would arrive there if you weren't appointed forwarder, but if by the time it gets down to the port logic, if you're not appointed forwarder, then you would not actually emit that native frame. It also says appointed forwarder and inhibition logic. So RBridges have various conditions under which they will inhibit a port. So this is really not the same as spanning tree blocking. It only affects native frames. If a port is inhibited, then even though you're appointed forwarder, you don't actually emit any native frames, and you don't actually input any native frames. And there's various reasons this can occur. One, for example, is TRILL hellos have a flag in them saying, I think I'm the appointed forwarder on the VLAN in which I've sent this hello. Well, so if an RBridge believes it's an appointed forwarder for a VLAN on a link, but off of that link it gets a hello from a different RBridge, and this other RBridge set also thinks it's appointed forwarder, you could have a loop if they both act as appointed forwarders. You could get frames decapsulated onto the link and then re-encapsulated if it's a broadcaster or multicast, for example. So under those conditions, you can temporarily inhibit the port. This has no effect at all on TRILL data frames or TRILL ISIS frames. Those are always, those can go through. So over on the right side, let's look at that. So we have TRILL data frames coming in. they go on up the right side, and then you decide what to do with them. Forward them to maybe a different port at the same switch, or whatever. And TRILL ISIs frames like link state PDUs and link state sequence number PDUs and things like that, they all go up the right side and are handled up there. And then if you emit link state or other TRILL data, or you're emitting a TRILL encapsulated TRILL data frame, that comes down the right side and it goes right out. So if you're sending a TRILL data frame, it goes down the right-hand side. It's not subject to any of this appointed forward or filtering or inhibition logic. A brief section on support of data center bridging. So you may know that Cisco coined this term data center Ethernet, and that initially meant four things: priority-based flow control, which is sometimes called per priority pause. I'll have more on these: enhanced transmission selection, congestion notification, and TRILL. So Cisco currently has sort of what they call a pre-standard version of TRILL called Fabric Path. It has the same basic idea of using ISIS routing to accomplish bridging, using encapsulation and a hop count. So the first three of these are data center bridging, and go into those a bit more. The goal is to get lossless Ethernet, that is to say no loss due to queue overflow. And you can actually do that with Ethernet within certain engineering constraints, like delay bandwidth product and stuff, just using the good old Ethernet pause feature, but that's pretty blunt. It interferes with things that are loss dependent for the flow control, like TCP. It can block high priority control messages. Obviously, it doesn't block pause control messages itself and stuff like that, but something like routing control or stuff messages could get blocked. And you have this thing where if a port on a switch is paused, then the queue can fill up, causing it to be unable to accept other frames, so it has to send pauses on all its other ports, and you have the spreading wave of pausing going through your whole network. So there's data center bridging provides actually two different answers to this problem. One is to consider different priorities to different pipes, so you have a per priority pause. You don't use it on the priorities where it might be a problem, for priorities you're using for TCP or the like, or ones you're using for urgent control frames. And you do use it for priorities where lossless flow is important, say some priority you're using for some fiber channel over Ethernet or something like that. Then there's also an ability to allocate bandwidth, which may give you better performance, and the idea is you would use that not to restrict anything with the highest priority frames, but you take the remainder of your bandwidth after the high priority frames, and you could carve it up between the different priorities as if they were different pipes. So you could say, okay, priority 4 gets 40% of the bandwidth, and that would mean that a priority 4 frame might actually be sent in preference to a priority 5 frame, a higher priority frame, if that 40% allocation wasn't used on that pipe at the time. So all this stuff is implemented in the ports. So you can actually do these on any kind of box, and the above two are easy to do on RBridges. It's just really part of the port logic. And because it's part of the port logic and really kind of occurs on a hop-by-hop physical basis, really for that kind of protocol, you could consider all nodes to be peers, because you have a queue filling up in an RBridge or a bridge or whatever. It can apply back pressure if that's a priority in which you've enabled per priority pause. It can send a pause traffic in that priority at the previous box, and so on back through your hop-by-hop physical chain. So the second answer data center bridging came up with is congestion notification. So the idea is to provide back pressure on the origin of a flow instead of doing things at a hop-by-hop queue basis. And so when your queue depth exceeds some bound, and this is all obviously spelled out in great detail in the 802.1 specs, you send a congestion notification message back to the source MAC address of the flow is the idea, perhaps a router or something, or an end station. And you send that, of course, in the congesting frames VLAN. So this is also enabled per priority, and you need to have a contiguous region where this is enabled in order to get useful results out of it. It's all defined how to do that. But this congestion notification message itself is usually sent priority 6. So you can label frames with the congestion notification tag if you want more information than just the source MAC address and the priority. If you're willing to have your flow granularity SBB by source MAC and by priority, you're fine. But if you want finer granularity, you can add a tag. The end station that's originating the frame can add the CN tag. And most of this is going to be implemented in the port logic. In TRILL, the CN tag, if it's present, goes inside the encapsulated frame. So it kind of follows the TRILL guideline that whatever frame would have been on the wire is now appears inside the encapsulation. And CNMs are really handled, it's like other native frames. They may be higher priority, but that's TRILL handles priorities. So if you have an encapsulated frame with a CN tag, this looks like this in TRILL. There's only one, you could really do all this really in port logic, but there's one minor problem, which is if you have bridges between RBridges, and these bridges presumably not know about TRILL, no bridge knows about TRILL currently, and there's a backup at one of these bridges, it will generate a congestion notification message based on the entire TRILL data frame. So it'll send that back to the previous hop RBridge and not to the original end station. And this is actually somewhat similar to a problem with other forms of encapsulation, like provider backbone bridges. If they get congested and want to generate a congestion notification message, they will tend to generate it based on the encapsulated message rather than the inner message. So an example here of the bridges shown here, one of those has a backup. It would generate a congestion notification message based on the TRILL data frame, which has a source address of the previous hop RBridge. So that congestion notification message would just go back there. So the only change in TRILL necessary for supporting data center bridging really is to be able to recognize those frames, to allow the congestion notification tag in the encapsulated frame, and to recognize a congestion notification message generated as shown on this diagram here, and be able to adjust that so that it's a congestion notification message back to the original source of the flow within the congestion domain, and will cause the appropriate constraints on the original generation of frames in that flow to relieve the congestion. So all this stuff in congestion notification and data center bridging assumes you have appropriate limits on the delay bandwidth product and do appropriate timing engineering and so forth. I'd like to go into some more details of some aspects of TRILL. Address learning. So TRILL actually has 5 different ways it can learn addresses. One is on receipt of native frame. So here you are, you're the ingress RBridge, you receive a native frame. You see the source address, you know what port you received it on, and by the time TRILL sees it, it will be classified as being in some VLAN by the 802.1q port of the RBridge, 802.1q-like port. So that's pretty straightforward. When you decapsulate a native frame, you can also learn. As you decapsulate the frame, you can observe the inner VLAN and the inner source address, so you know what the actual source address of this frame was. And you can also see in the TRILL header the ingress RBridge. So you can basically assume that that source address in that VLAN is a directly connected end station for that ingress RBridge. So if you then later see a frame which is addressed to that address in that VLAN, you can know that you can use what was the ingress for that frame as the egress to get your frame delivered to that end station. There is the optional way to transmit this information through the control plane, which I have another slide on, but basically you can learn VLAN, address in that VLAN, and which RBridge nickname is for the RBridge that has that address connected in that VLAN. You can learn that through the control protocol. And you can learn things via layer 2 registration protocols, 802.11 association and authentication perhaps. And that kind of way may be more reliable. Some of those layer 2 authentic registration protocols may include some cryptographic authentication or something like that, giving you a higher confidence than just observing an address on a frame. And lastly, of course, you can always manually configure addresses. So this end station address distribution information protocol, it's a VLAN scoped way where an RBridge can distribute through this protocol information about attached end stations to other RBridges. So the transmission is very efficient because it's tunneled through all the transit RBridges, encapsulated just as if it was a normal multicast data. So only the RBridges which are have end stations connected in that VLAN would ever pay any attention to these frames. So So it's really intended for use for attachment data that's either secure, so you want to communicate it securely, or that changes rapidly. So I didn't mention, but actually the IS control messages and also the ASADI messages can actually have a message authentication code in them. So if you've learned some attached end station through some cryptographic registration protocol that it went through, and you want to really reliably transmit that to other RBridges, if you use ASADI, you can also include a message authentication in the ASADI frames. And that way, the other end, when they verify that, has a really high level of confidence in that end station address attachment information. So, and also if something changes rapidly, you have to want to avoid the problem of something being black holed because you're remembering some old address you learned, because it's skipping around between being connected to different RBridges. If you use ASADI to distribute stuff, then that can update the address attachment information more rapidly in all the RBridges. It is an option. You need to have to be implemented on the RBridges and needs to be enabled. By default, RBridges simply learn from the data plane, and they are required to learn from the data plane unless that's specifically disabled. And the ASADI needs to be enabled to learn from the control plane. There's no particular, so I say the source RBridge selects which address. It doesn't have to advertise all the addresses it knows about for attached things. Other RBridges can still learn from the data plane for some of them. You might choose to use it only for certain addresses which it's more confident in, or which are which the attachment will be short-lived. Because when it's using ASADI, it can also transmit the information that some address is no longer attached. When it sends out the update, it can remove an address from that to the data it's sending. So unless there's no particular advantage for using this for if you have like a bulk of stuff you learn from the data plane. Let's say you're an RBridge and you have a bridge LAN with 10,000 end stations, or maybe 10,000 virtual end stations on it. So you learn 10,000 end station addresses through observing these data frames arrive. Well, if you wanted to, you could take that wad of data and you could shove it through ASADI, but it's not clear that that's really too much of an advantage. You could just let other RBridges learn from the data plane. On the other hand, if you have some addresses you believe are especially reliable, or which you have reason to believe are short-lived attachments or something like that, then it might be a good idea to advertise them through ASADI, so you can get the reliability of sending it through secure frames, or in the responsiveness of being able to update and other RBridges more rapidly about the existence and then the non-existence of the attachment. So reordering is always an interesting question. RBridges are required to maintain frame ordering internally for a particular priority, and there's sort of an escape clause. If you are clever enough to categorize frames by flow, then you only have to maintain things within that flow. So if you want to analyze IP frames by IP protocol type and ports and so on and so forth, then you could reorder between those flows if you wanted. When multipathing is used, all the frames for an order-dependent flow is be sent on the same path of unicast, or on the same distribution tree if multicast, or multi-destination. It is the case that with unicast, with RBridges, unicast reordering can occur briefly when a destination address transitions between known or unknown, or if there's a topology change. And actually, bridges typically reorder when an address changes between known and unknown, because many bridges put unknown multicast frames on the multicast queue. You can essentially eliminate that by for that transition by using keep lives, using ASADI to distribute more rapidly. You can do more distribution trees to make the unicast and multicast distribution similar, or you can use configured addresses. So like FCOE plans to solve this problem by using keep lives. That's why they're provided there. Loop avoidance, a critical factor for things at layer 2. If you look at various possible loops there could be, you can categorize them into three groups. One is a TRILL data frame loop, which the frame remained TRILL encapsulated all the way around the loop as it looped around. A hybrid loop where the frame was repeatedly encapsulated and decapsulated, or a native frame loop, in which the frame was never encapsulated. Well, the last one is easy to take care of for TRILL because it has nothing to do with TRILL. If it hits an RBridge, a native frame hits an RBridge, it gets encapsulated. So if you have the last problem, you must have like problems with your bridges or something. So really the first two I'm going to talk a little bit more about, because those are the ones which really are related to TRILL. So TRILL data frame loops, well, what could be the, what could really happen? Well, if you have unicast frames, it's not clear why there would be other than a brief transient loop. But if there was, you got a hop count, and so nothing that bad can happen. And unicast frames can follow varying path as if there's a routing transient happens. As long as you have an adequate hop count, they can generally still get through, even if they do essentially alternate forwarding during their path. They're really not too dangerous. Multi-destination frames are potentially much more dangerous because you can have forks in the distribution tree, and so you could have a multiplying number of such frames. So they do a reverse path forwarding check, in particular when a multi-destination frame arrives, a multi-destination TRILL data frame arrives on a port. It's checked whether that port is really part of the tree, and then much more closely, it's checked whether assuming that frame was ingressed by the indicated ingress nickname in the TRILL header, is this the input port on which you would expect to receive it, given your current knowledge of the distribution trees? If it seems to have arrived on the correct port, everything's fine. If it did not arrive on the correct port, then the RBridge will not forward it. And as an extra stopgap, multi-destination frames also have a hop count. So should something go wrong somehow, they will also time out. They'll also count out in the hops and be discarded. So what about the hybrid, the other case, the hybrid TRILL data frame loops? This assumes that around the loop somewhere, the TRILL data frame is being decapsulated onto the link by one RBridge, and then picked up and re-encapsulated by another RBridge. This essentially assumes that you have two appointed forwarders on that link for the same VLAN that are active at the same time. And that's why there are these extra careful steps, why TRILL ISIS hellos are careful to make sure they get through, and why there's the various cases in which you will temporarily inhibit a port because you believe there's some chance there might be a circumstance like this. So that takes care of those cases. So this is basically some more text that is added about inhibitions. That's really stuff that I said before. And it's good to keep in mind that this inhibition of a port in TRILL really only affects native frames. That does not affect TRILL data frames. TRILL data frames have essentially been tamed. They've been encapsulated. They're under control. There's not a problem. Native frames, you got to be a little more careful about native frames because they haven't been encapsulated or controlled by TRILL yet. So people may remember Algorithm. If you just search on the net for that, it's very easy to find. It was written by Radio Perlman 25 years ago for spanning tree. So since Radio basically invented TRILL and RBridges, she thought clearly you needed to have a new poem. So instead of writing it herself, she asked her son to write it. And this is the poem. I hope that we shall one day see a graph more lovely than a tree, a graph to boost efficiency while still configuration free, a network where RBridges can route packets to their target LAN. The paths they find to our relation are least cost paths to destination. With packet hop counts, we now see the network need not be loop free. RBridges work transparently without a common spanning tree. Oh, the last thing I'm going to cover is standardization status and the references. Some references that may be useful to you. So as usual, standardization efforts take much longer than could possibly be reasonable. I mean, how could it possibly take 5.5 years to take this simple, I mean, the very first slide is a very simple concept. I mean, it does, transparent forwarding by just taking the native frames, encapsulating them with a hop count, routing them by normal routing techniques, decapsulating them, delivering them. How hard is that? Well, anyway, the first TRILL working group meeting was in March of 2005. The working group was essentially finished with the base protocol draft in December 2009, and almost exactly 5 years after the first TRILL working group meeting, the IETF approval of the TRILL base protocol as an IETF standard was announced on March 15th of this year. So there are various assignments that have been accomplished. There's the TRILL and the layer 2 ISIS ether types have been assigned. The block of multicast addresses for TRILL is assigned. The TRILL network layer protocol ID is assigned. Currently, the only thing left is the ISIS code points and data structures. They've been actually quite stable for a long time, but final ratification has not yet occurred. They have been stable enough that there are plenty of implementations going on. In fact, there has been a plug fest demonstrating control plane interoperability of TRILL implementations. That was at the beginning of August, month before last. And there's work underway to plan a second TRILL Plug Fest. There's ongoing work related to a MIB, TRILL over PPP links, the VLAN mapping, and DCB, OAM development, and TRILL header options and stuff like that. Quite a bit going on. So, references. Here are the some newer references. The very first one there is the TRILL base protocol specification, the draft that was approved as a standard. So it has not been published as an RFC yet, although it's in the RFC editor's queue because it's pending the final ratification on the ISIS code points and formats. Second item here is the draft explaining the VLAN and priority region mapping mechanism that I described earlier. There is a MIB draft. I expect that MIB draft will be probably approved fairly soon. There's a draft on how to send TRILL over PPP if you want to have the link between two RBridges to be a PPP link. Some older references. There is an RFC from some time ago on the TRILL problem and the applicability of TRILL. There's the TRILL charter. The current TRILL charter is way out of date, but it's what we have. And that's what the first pointer there is. There is a proposed new charter, which is going through the process slowly. And there's an original paper which was written in 2004, as I say, when things started, by Radio Perlman. So that is my presentation, and I would be happy to entertain questions. Yeah, pretty much. It's not restricted to data center in any particular way. You could use it in a variety of cases, but most people who are working in this area are assuming that they're going to use it in a data center. You know, the applicability RFC here says that it was not a design goal to scale larger than existing bridge lands. But the estimates it gives for existing bridge lands is actually very large, and it's not prohibited from scaling. So I believe that through the use of ISIS and so forth, that in fact will scale larger than certainly scale larger than Spanning Tree. Let's put it that way.
So
Yes.
Through the discovery mechanisms, every RBridge knows all the MAC addresses in the campus, in the RBridge campus.
Every MAC
Therefore, it maps that to like egress.
No, each RBridge knows the topology. It knows the MAC addresses of its neighbors, and it knows the MAC addresses of its, if it has directly attached end stations. Let's assume it's a core RBridge, it's a transit RBridge. There's no end stations involved. All it needs to know is the MAC addresses of its neighbors. When it receives a TRILL data frame, all it needs, assuming it's unicast, which is a simpler case, it just looks at the egress RBridge nickname. All it has to do is know which port to send that out of. It swaps the outer headers and forwards it just like a router does, based on that egress RBridge nickname. Only RBridges with attached end stations need to know MAC addresses of end stations. It's like asking whether, if you, let's say you have a network of IP routers, okay, and for whatever reason you have a fairly rich mesh of, a bunch of IP routers, and there's an IP router in the middle of this hierarchy. You need to know the MAC addresses of every IP router. Well, of course not. It doesn't give a damn. I mean, all it needs to know is how to get to the. It may need to know something about its neighbors. May do ARP and stuff like that. But why does it care about the MAC address of a router a couple router hops away? RBridges are really routers. They don't need to know anything about the MAC addresses of other RBridges unless they're an immediate neighbor. And the only reason they need to know the MAC addresses of end stations is because they need to be able to map those into nicknames for routing purposes, and then and when they get a frame to decapsulate, they need to know which port to send the frame out of. So when they decapsulate this original native frame, they need to look at the MAC address and the VLAN to figure out which frame to send it out in native form to the destination end station.
Do you support Q and Q in the payload?
That is not, there's no explicit provision for that in the current version. There is some controversy about what to do about that. What it says is that considerations involving S tags, service tags, are beyond the scope of this document, is what it says. So there's no prohibition from being able to do that, but it's not specified in the existing document.
And second question, what happens if an RBridge has multiple connections to the same bridged, either same bridge or same traditional bridge topology?
You can have multiple connections to the same bridge LAN or whatever. So that's not a problem. There's a section on that. You can have two RBridges with multiple parallel connections and so on. And you have to go read the exact details. There's specific sections in the base protocol specification on how to handle that. It has to be sure that if there's unicast traffic, it can't be a problem, because unicast traffic is always addressed to a unicast MAC address of a specific port. So it'll just receive it on the port it's addressed to. If the if you have multi-destination traffic that's sent to a, then it will be forwarded using the all ISIS RBridges multicast address. Then it will receive it on all the ports that are hooked to some bridge LAN, possibly, or at least some link.
Well, unicast traffic that's native wouldn't be addressed to an RBridge port.
That's correct. So the way that works is that it is the appointed forwarder logic. So so native traffic is in some VLAN, and there's only one RBridge which is appointed forwarder, and that RBridge will in fact receive the native traffic on multiple ports, perhaps if it's multiply connected. But so it just needs to know which port it wants to accept it on. It's really an internal affair of that RBridge. And if it felt like it, it could do something bizarre like accept that traffic in VLAN 7 on two different ports, depending on the bottom bit of the MAC address of the source. So only, native frames from source MAC addresses that are odd would be accepted on one port, and ones that were even would be accepted on another port, as long as it can keep the flows separate, like it says in Ghostbusters, don't cross the flows, and you'll be fine.
Hi, Louis Lee from Equinix. If you want to think beyond just a single data center or even a campus, I can see this useful in a metro area where the inter-building links are very expensive and has a large operational cost compared to just ports within the data center. So this will let you make use of those dead links that your spanning tree would be blocking, even though you have to buy large enough links for failover. So that's another consideration, another use for TRILL beyond just inter-campus single data center type uses. One question I do have, I didn't notice how big is the new header that's added on, so because we have to consider then the MTU size.
Sure. The TRILL header with the ether type is a total of 8 bytes. There's 2 bytes for the ether type, 2 bytes for the ingress nickname, 2 bytes for the egress nickname, and then 2 more bytes, which include the hop count and the option size and the mbit and the version number, which is always 0 currently, and so on. So there's a total of 8 bytes in the TRILL header. I think it's reasonably economical. That's another reason for the nickname mechanism, is to provide, essentially what it says is those 16 bits are an abbreviation for the 48-bit ISIS system ID of each RBridge. Other questions?
Hi, Jason Ackley, Rackspace. 2 questions, actually. First one, on the length of time to develop the standard, how much of that was kind of split between new stuff and interoperability? And then the second question would be just a general status update on the Plug Fest and what happened, and any new stories from that, anything that broke.
Okay. Why did it take so long? So 18 months ago, actually more than 18 months ago at this point, we thought we were finished. But needless to say, people were developing it. I might comment that there is a open source implementation of TRILL by Oracle for Solaris, which is an open source operating system. And anyway, they were deploying a version based on the, I don't know if you noticed, the TRILL draft is -16, that's the 16th version, actually 17th because it started with 0. They were implementing the -10 draft, which we thought was like really close to final. And it turned out that it was not robust to limited MTU links as a whole TRILL hello size thing. So that pushed, out considerably further. The earlier, there was a lot of, the early design phase was not too bad. Didn't take that long to get the general outline of how things would work. But it did take a while to nail down the details, and then there was this hiccup which required some revisions to add the MTU robustness. And as part of the side effect of that, TRILL ISIS now includes these MTU probe and ACK, so it can measure and report the MTUs of links. So you could conceivably use that for traffic engineering. So you could restrict, send jumbo frames over shortest path routes that were restricted to links that could accommodate jumbo frames and so on. So it has some collateral advantages as well. On your question on the Plug Fest, I actually attended, it was a 3-day Plug Fest, and I attended things for 1 day. And there were, with no real particular problems, people were sending TRILL hellos and link state packets and CSMPs, and they're sending, appointing each other a forwarder on the link. And there's one feature it has is if you have an RBridge port, I didn't get into, an RBridge port which is a pointed forwarder, so it's handling all the native traffic for some VLAN, and that status is taken away from it. So some other port, other RBridge port, different RBridge probably, on that link is now the appointed forwarder. There can be a slight problem that any bridges in that link may have learned that this port, or this link, that path was the way to various remote addresses and so forth. So the address learning of bridges is basically assuming continuance of that appointed forwarder state. So if that port is receiving any BPDUs, so it has reason to believe that there's a bridge out there, then it's a should, and I think everybody does it, send out a topology change BPDU. Say, hey, you bridges out there, there's just been a change in who the appointed forwarder is in the RBridges. So that was actually being tested, and the various RBridge things at the Plugfest were successfully sending those topology change BPDUs to people were like manually configuring their priority to be their designated RBridge up and down, so that it got swapped back and forth and pointing different appointed forwarders and stuff. But there weren't a particularly large number of participants, but it all worked well. And so there's a white paper, and the white paper was originally supposed to have been issued last Friday. And I was hoping I could have copies of the white paper here. It's not very big. It's just a 3 or 4 page document on the interop and stuff. But I guess it has to be cleared by the marketing departments of all of the companies that participated. And there's one of them that hasn't gotten back yet to UNH IOL, so I don't have the white paper, but any day now, maybe. Any other questions? Okay, thank you all. I'll be around today. I'll be around during the day tomorrow. There is tomorrow a debate about TRILL and shortest path bridging, which was an earlier tutorial today. I'll be here, as I say, tomorrow through that debate, and a little while after that debate, but I'm going to be leaving, so I won't be here later in the week. So feel free to come up to me in the hall or whatever, if you have any questions, and ask me while I'm still here, or send me email if you feel that. Okay? Thank you.